Yes. So welcome everybody to the second talk. We have Martin Sloth from Southern University, Denmark, and he's going to talk about resolving the Hubble tension with new early dark energy.
Thank you. So this is work in collaboration with these very nice and fantastic collaborators down here. It's a long period of work, so there's a long list of collaborators also. So I'm going to discuss the background for this and then the latest developments towards the end. So I assume that you're all familiar with the lambda-CDM model and the model that we also sometimes call the concordance model or the standard model of cosmology. And that's, of course, because there is a strong evidence for this model based on CMB observations, baryonic acoustic oscillations, and supernova observations. So if we go back, for instance, to the situation in 2010-ish, so that's what, 15 years ago about, then we see that the CMB observations and the BAO observations and the supernova observations nicely converge on this gray ellipse here, which is the lambda-CDM model with say 25% cold dark matter, 70% cosmological constant or dark energy, and a spatial flat universe. And so this is also why it's called the concordance models, because all the measurements are in concordance with the lambda-CDM model. So now if we think the lambda-CDM model is the final answer to how we describe the universe, of course, we would assume that as we make more and more precise measurements, so as we collect more and more data, the error bars on the BAO measurements, the CMB measurements, and the supernova measurements will shrink, and they will converge on this gray ellipse that characterizes the lambda-CDM model. On the other hand, if the lambda-CDM model is only a good approximation to the universe, and there is a more precise or deeper microphysical model that is richer below the lambda-CDM model, we would assume that as we reach more and more precision, some discrepancy between these measurements is starting to show up. So now we are not in 2011 anymore, we are later. So we can actually ask this question and we can play the movie forward and see what actually happens. So with a little bit of suspense, let's see what happens. So if we go to 2020, we see that indeed the error bars has shrunk, and they have shrunk more or less around the point that we expected, except that the CMB measurement shows a little bit of tensions with the BAO and the supernova measurement. So if we put the lambda-CDM model here, it's kind of like on the edge on all the contours. It's a 2 sigma tensions more about within the lambda-CDM model here. Of course, that's not a significant tension, so it's not like we would kind of, be alarmed to the extent of giving up the lambda-CDM model at this point. However, we can also plot the data in another plane where we have the Hubble constant and the sound horizon of the primordial plasma. So we have a primordial plasma of baryons and photons until recombination, and the sound speed of the plasma waves in this plasma tells us how far a plasma wave can have propagated from the beginning of the universe, from Big Bang and until recombination, and that distance is the sound horizon. So that sound horizon is given by the properties of the primordial plasma, so it's given by the properties of the early universe, so it's given also by the content of radiation, matter, and cosmological constant. And then we have the Hubble constant on the left side, and we see that there is in this plane there is a stronger disagreement between the different measurements. So if we take the Hughes measurements, which is a supernova measurement of the Hubble constant, it's in agreement with the BAO measurement, but with a smaller sound horizon than what we get from the CMB. On the other hand, the CMB is in agreement with the BAO measurement, but not with the supernova measurements. And indeed, there is roughly, at this point, 5 sigma discrepancy between the supernova measurements and the CMB measurements. So, what is going on with this Hubble constant? So maybe we can also take another historical perspective. So we can take a perspective where we look at the measurement of the Hubble constant just after the discovery of dark energy by the Hubble Key project. And we see that at that time, with the most precise CMB measurements at the time, basically the error bars were so big both on the CMB determination of the Hubble constant and on the determination of the Hubble constant using supernovas that they were in agreement. And we can go back to the first measurement we had before, the first concordance measurement we had before from 2010. And we see that also here there is a rough agreement between the first Hughes measurement and the WMAP measurements because, again, the error bars are big. And so everything agrees within the error bars. But now, as we play the movie forward from 2010, we see that the measurement starts to diverge again between CMB and Hughes, as we also saw in the other plot before. And so this is a problem, no? So this means that if we look at these two types of measurements, we can think of the CMB measurement as being an early time measurement because the CMB is formed at recombination, which is only 380,000 years after Big Bang. And in order to propagate that measurement forward until today and use it to determine the Hubble constant, of course, we need a model for the universe and a model for how to, make the link between what happens at recombination and today. And so the early measurements, the CMB measurements, assumes the lambda CDM model. So we can either think of it as an early measurement, or we can think of it as a measurement that assumes the lambda CDM model. On the other hand, we have the Hughes measurement, which does not assume a lambda CDM model because it's a measurement in the near universe up to redshift 1, a little bit more, 1.5. So it's not, it doesn't need to assume a full model of the universe. And so we can think of this late measurement in the local universe, or, well, not local in the sense, I mean, it's in the Hubble flow, but not, but a late time measurement in the sense it's small redshift, so local in that sense compared to the CMB. That measurement doesn't assume the lambda CDM model. It's kind of more model independent. And so you could also think of these late measurements as being measurements that are model, not completely model independent, but as model is independent as we can think of in this context, as reflecting the actual universe. So we have the lambda CDM measurement, and we have the status of the actual universe in the late measurements. Of course, at this point, again in 2020, people were not, they were concerned, but not panicking over this Hubble tension, because in addition to the Hughes measurement using type 1a supernovas, there were also a measurement by the Chicago group using the Red Giant branch. And that measurement gave a smaller value of the Hubble constant. And this value here is kind of in between the one from Hughes and the one from CMB, and kind of in agreement with both. And people were thinking, maybe still to some extent today, but at least at that point, we're thinking that, okay, maybe there could be some systematics in the Hughes measurement, some unknown systematics that isn't understood. And, and that could explain the Hughes measurement as being basically an outlier, and maybe the correct measurement is more like this the Chicago group measurement, and which is within the error bars in agreement with the CMB measurement. And so there were this kind of way out where in some ways one could imagine that with some unknown systematics in the Hughes measurement and so on, maybe everything could be in agreement still. If that was the case, of course, you would expect that as you make more and more measurements again, more and more precise measurement, and understand the systematics better and better, collect more data points, investigate all the sources of possible systematics, then you would expect that the data points here would move more to the left and be in agreement with the Chicago measurement and the CMB measurements. And now again, we can ask the question, because we are not in 2020 anymore, what happened? Did all these measurements move to the left, or did something happen to this measurement? What happened? And what we see is that with the James Webb Telescope and more data again, the red giant measurement moved to the right and becomes in agreement with the Shoes measurement. And so the Hubble tension is becoming stronger, and it's becoming more and more difficult to explain it away with unknown systematics, especially also because the observations by the James Webb Telescope is consistent with the observation using the Hubble Space Telescope. So this is the situation now. Of course, one could still, one could still worry about unknown systematics in the late measurements, but it's becoming harder and harder to find some kind of systematics that can explain away all these measurements at the same time. So instead, we can ask ourselves, what could it be that the CMB measurement is wrong and it's not the local measurements that are wrong? Could it be that the assumption of lambda CDM is simply too crude an approximation to describe the universe? And if we find a better model that to describe the universe and to fit the CMB with, that the CMB measurement would move closer to the measurement of the Hubble constant in the local universe. And this is what we are working on, and I'm going to explain you in this talk that if you assume a new phase of dark energy in the early universe, that means after BBN but before recombination, such a new phase of dark energy can explain the CMB measurements with a larger value of H0 that brings agreement between the CMB measurements and the supernova measurements. And so I'm going to explain to you how this works. So let's return to the plot before. It's an important plot. So we see here again the sound horizon and the H0, the Hubble constant measurement in a plane. And we see again the BAO measurement in the green line and the CMB measurement in the blue ellipse here, the BAO measurement in the green line, and the Shoes measurement in the orange band up there. So, okay, so it's important to understand that the disagreement between the Planck CMB measurement and the Shoes measurement of the H0 is a model-dependent statement because the Planck measurement of the Hubble constant and the sound horizon assumes the lambda CDM model. On the other hand, the BAO measurement and the supernova measurement does not assume the lambda CDM model. And the BAO measurement by itself constrains the product of H0 times the sound horizon to be a constant. So that's what gives this green band here. So that means that if you want the CMB to become consistent with the supernova measurements, you need to move this blue ellipse along the green band up to the orange band. So this means that as you raise the H0 value to bring a concordance with the supernova measurement, you need at the same time to lower the sound horizon within your model, this new model that you are trying to explain the CMB with. To lower the sound horizon means that you need new physics before recombination, because the sound horizon again is how far a plasma wave can have propagated from Big Bang until recombination. So it's an integral over the sound speed from Big Bang until recombination. That means that there is no contribution to it after recombination. So to change it, you need new physics before recombination. So in order to solve this, to find a new model that is a more precise description of our universe that can bring agreement between CMB and the supernova measurement, we need to add new physics before recombination in such a way that the sound horizon is lowered and the Hubble constant is raised. Oh, sorry. So let's see how you can do that. So one way you can do it is, again, to assume that you have an extra component of some unknown matter energy that is present before recombination, and which raises the Hubble constant before recombination, and at the same time lower the sample horizon. So a natural candidate for such an unknown component, extra new component of matter or energy, is dark radiation. So assuming that there is some extra dark radiation is a very simple natural assumption. However, if you assume some extra free streaming radiation, dark radiation, then that is not going to reduce the tension enough, simply because the amount of free streaming relativistic radiation you can add is highly constrained. And this is because if you add radiation, it will be some radiation which is there also when the ordinary radiation is there. And so it will lead to some extra damping on small scales, and some, if it's free streaming, also some anisotropic stress and so on, effectively. And that will be constrained by CMB measurements. And so it's basically constrained to play a very little role, and it can only reduce the tension marginally. So this is not, although it's a very simple idea, very simple addition to the lambda CDM model, it's not going to solve the Hubble tension. Okay, so then people came up with a more sophisticated idea, which is the idea that you have early on some scalar field that is frozen in a almost flat potential, which means that it behaves more or less like a cosmological constant at that time. That means that it very rapidly become important compared to radiation in the radiation-dominated epoch. That means that it can be very subdominant for most of the period of radiation domination, only to become important just before recombination. And then, if it's tuned correctly with the mass and everything, it can start oscillating just before recombination and decay away just before recombination. However, just before recombination, we are now in matter domination. I mean, matter is going to take over just before recombination. So to have it oscillating in a quadratic potential is not good enough, because then it will behave like matter and it will be present also during recombination and after. So you need something where the field is oscillating in a potential that is steeper than quadratic around the minimum. A 5-4 potential around the minimum is also not good enough, because then it will behave like radiation when it oscillates, or it will redshift like radiation when it oscillates around the minimum. So what you really need is something which is a 5-6 potential around the minimum, so it behaves effectively as a stiff fluid when it starts oscillating and redshift away very fast. Now that's a problem, because that's very fine-tuned, because that means that if you Taylor expand this potential around its minimum, the first two terms in the Taylor expansion has to be fine-tuned away, okay? So this works phenomenologically, but from a theory point of view, this is not maybe how we would expect the universe to look. So therefore, we are motivated to find, building on this kind of phenomenological success of this idea, to find some microphysical description which is more natural from a particle physics point of view. So then the idea is to look at what we call a fast triggered phase transition. So essentially assuming that there is an extra degree of freedom that triggers a fast phase transition. So I mean, one way of thinking of it is to have a bowl of boiling water or initially not boiling water, but where you fastly crank up the flame and trigger a phase transition in the water. So the effective model of this is that you have a force vacuum that decay away quickly, because there is a new degree of freedom that triggers a phase transition, and then you have an early dark energy component that we now call a new early dark energy component that quickly disappears before recombination in a triggered phase transition. So this is a framework for solving the Hubble constant. There are different microphysical descriptions of how such a fast triggered phase transition could happen. So we have different models within this new early dark energy framework. And some of the microphysical models within this framework are what we call cold new early dark energy, where the phase transition is triggered by a second scalar field. So that would be a little bit like how inflation ends. So you have a field in a force vacuum where the decay of the force vacuum is triggered by scalar degrees of freedom. Then we have hot new early dark energy, where it's a non-vanishing temperature in the dark sector that triggers the decay of early dark energy. So this would be more like how we think of the Higgs phase transition, although in the electroweak phase transition, of course, it's not first order to what we know at least. But there you have thermal corrections to a scalar field potential that triggers a phase transition. So that would be like hot new early dark energy. And then you can have a kind of like hybrid new early dark energy where there is, say, a second scalar field, for instance, that triggers a second order but rapid phase transition. Or you could think of curvature or other degrees of freedom as triggering this phase transition. But what we have studied the most is the cold new early dark energy model and the hot new early dark energy model. So these are the ones that I'm going to focus on now. So here is the general qualitative picture of how it works. So you have the false vacuum energy, and then you have this extra degree of freedom that triggers a change in the effective potential and opens up a true vacuum. And as this true vacuum opens up, you have, in this case, a first order phase transition where you rapidly nucleate bubbles of true vacuum that percolates, collides, and percolates. And once you are in the false vacuum, you have essentially an equation of state of -1. So you have some false vacuum energy that is your new early dark energy with an equation of state of -1. And once you tunnel and you start percolating, you have an equation of state with an between 1/3 and 1, because once your vacuum decays, the free energy is converted partly into an isotropic stress that sources gravitational radiation. So you have a mixture, I mean, very broadly, very generally, and very qualitatively, you will have a mixture of something that is radiation and something that is anisotropic stress light, and which behaves more stiff. So you will have very generally an equation of state that is between 1/3 and 1. Okay, so this is just to give a very general comparison between these two models within the new early dark energy framework, the cold NED and the hot NED model, where in the cold NED model, the trigger of the phase transition is an ultralight scalar field that deforms the potential here. So the extra degree of freedom that deforms the potential is an ultralight scalar field that becomes dynamical around recombination. In the hot NED model, as I mentioned, is a thermal correction to the potential. So it's a non-vanishing dark temperature that deforms the potential. In the case of the cold NEDE model, when we fit the model to, and I will come back to why this is the case, but when we fit the model to, this is just an overview, but when we fit the model to the CMB data, we find that the cold NED model to solve the Hubble tension, there the phase transition has to happen very close to matter radiation equality at a redshift of 10 to the 4, where in the hot NED model, the phase transition happens earlier after BBN, but well into the radiation-dominated regime. And this has partly to do with the equation of state after the phase transition, and I will also explain later why the equation of state after the phase transition is different in these two models. But in the cold NED model, you have this diffish kind of equation of state after the phase transition of 2/3, while in the hot NED model, you just have radiation domination. You are just decaying to radiation. Okay, you just have radiation after the phase transition. Okay, so also the natural classes of models that you will implement these models into are different. So because here you have an ultralight scalar field that becomes massive and becomes dynamical around recombination, then you will naturally embed this kind of model into action-like particle scenario. So you will protect the light masses with approximate shift symmetries and this sort of things. While in the hot NED model, you have the thermal corrections to the to a Higgs-like potential. So it's really like a dark Higgs model if you want. The physics that lowers the sound horizon in these two models is different. In the cold energy model, because the decay happens so late, it's really the onset of, I mean, of the importance of the dark energy component, the new early dark energy that becomes important, that contributes to the sound horizon integral and lowers the sound horizon. While because the decay happens earlier in the hot energy model, it's the dark radiation that you are decaying into that is contributing to the sound horizon integral and lowering the sound horizon. And as we will see, you need some self-interacting dark radiation. So we need some non-abelian gauge group with self-interactions and a self-interacting dark radiation in order to avoid this anisotropic stress component in the free streaming radiation, but also it comes naturally when you have a phase transition from some spontaneous symmetry breaking in a non-abelian gauge group, as we will come back to later. And this is this additional self-interacting dark radiation after the phase transition that actually lowers the sound horizon in this type of models. And so actually, as a class of model, the cold NADE model is a natural alternative to the original EDE model. But it's kind of more grounded in natural particle physics, if you want. While the hot NADE model is actually more like a UV completion of what we call self-interacting dark radiation models. And why you need to think of it as a UV completion is also something that I will come back to. Okay, so this is just a brief outline of how these models look. Here is a little bit of a picture of this, again, of this effective cosmological model, where you have the equation of state of the new early dark energy component that is initially -1, and then at the time of the phase transition that we can assume to be instantaneous, the phase transition happens very rapidly due to this trigger mechanism. It instantaneously changes to an equation of state after the phase transition, which is between, as I said, 1/3 and 1. Of course, when you have this instantaneous phase transition that instantaneously changes the equation of state, perturbations during the CMB epoch will feel this change in the equation of state in different ways, or feel the phase transition in different ways. And of course, CMB is perturbation, so we are very sensitive to how perturbations are affected due to a phase transition during the CMB epoch in this way. So we need to calculate the effect on perturbations very carefully. And so the first thing is, of course, that the perturbations will feel this instantaneous change in the equation of state. So this is relevant for the CMB. And also, the phase transition will not happen at exactly the same time everywhere, because the trigger field itself will have perturbations. If the trigger field is a scalar field, there will be adiabatic perturbations in the scalar field that will make the scalar field trigger the phase transition a little bit different times in different places, adding additional perturbations after the phase transition. The same thing if it's a temperature, there will be adiabatic perturbations in the temperature, the dark temperature, that will also trigger the phase transition at a little bit different times in different locations. And so one needs to take into account these things. And this we do by basically matching the perturbations across a matching surface, where the matching surface is now determined by the trigger. So the matching surface could be a surface of constant trigger scalar field, or it could be a surface of constant dark temperature. And then we match the perturbations across this matching surface using Israel junction conditions, for instance. And this is a technique that was used to phase transitions during inflations, also by Derul and Mukhanov, and at the end of inflation, by the way, also to show the constancy of the curvature perturbations at the end of inflation. And then there will be also isocurvature perturbations from the finite size of the bubbles as they collide. But we will assume that this phase transition due to our trigger mechanism is very rapid, so that bubbles are still very small when they collide and percolate, which means that these isocurvature perturbations are in smalls that are irrelevant for the CMP. Okay, so we have seen that through the choice of the matching surface, the perturbations after the phase transition depends on the detail. It depends on the choice of the trigger, the microphysics of the phase transitions. And since CMB and large-scale structure depends on the initial perturbations after the phase transition, we can use precision measurements of the cosmic microwave background and large-scale structure to discriminate between the microphysical realizations of new early dark energy, whether it's cold new early dark energy or hot new early dark energy. These models will have different predictions because they carry different perturbations, and they will again be very different from the original early dark energy model in detail. So the XE early dark energy model, or whatever people call it, it has different names. Okay, so let's look a little bit more in details at the cold new early dark energy model, where you have two scalar fields. You have a scalar field, which we call the NAD boson, that undergoes the tunneling. The mass scale is set by the recombination scale because it happens slightly before recombination here, so it's the EV scale. And then you have the light trigger field that triggers the phase transition, which has to be an ultralight scalar field because it has to become important around recombination. And this hierarchy is technically natural, as long as the coupling is the lambda twiddle is small enough, and you can check that this is all self-consistent. And also you can embed this in a two-action model, or so a model where you have two actions where these mass scales are technically natural and protected. So in this case, the trigger surface is the surface of constant scalar field, as I said, and you can embed this model into a modified version of class, which to simulate the perturbations, the CMB perturbations in this model, and fit it to Planck data, for instance. And what we have done is to indeed do this work, implement this model into a modified version of class that we call trigger class, and fit it to CMB, BAO, and supernova data. And what we find is that it can fully resolve the Hubble tension. So this is using Planck. Okay, and we also use not the newest ACT data. This is a little bit older work. So this is using the previous ACT data and also SPT data. And we find that you can indeed go to a very large value of H0 within this model if you have a non-vanishing new early dark energy component. And there is, if you use all the data, the SHUS, Planck, CMB, and the BAO data, you get a 4.8 sigma evidence for new early dark energy, cold new early dark energy. And yes, so I mean, yeah, I mean, if you assume the Hubble tension is there and you trust the data and you do this job, then this is what you find, and you are happy. But very interesting, because you have this extra component of new early dark energy that suppress structure a little bit. You need to have a blue spectral index, a little bit more blue spectral index, to compensate the damping on small scales. And that means that because you get a little bit more blue spectral index in these models, if you look at it with inflationary glasses, then the Starobinsky model is no longer a favored model of inflation if you want to solve the Hubble tension at the same time. Because if you look at the original story, so if you look at the Planck constraint in the spectral index versus the tensor to scalar ratio plane, then the green contour here is the original Planck and bicep constraints. And you see that the Starobinsky model, which is the purple line here, fits very well with the lambda CDM model using Planck and bicep data set. But if you want to if you add also the SHUS data and want to solve the Hubble tension using the NED model, you get this more blue spectral index that rules out the Starobinsky model, and instead a curvaton model would be the preferred model of primordial fluctuations to give you the initial spectral index. So it has so the Hubble tension has severe consequences for our understanding, not only of what happens in the CMB epoch, but also for the initial conditions of the CMB perturbations and our understanding of inflation. Okay, so let me discuss the other model, the hot energy model, which is more similar to what we know from standard phase transitions in cosmology, like the Telluric phase transition, QCD, and recombination, and so on, where you have thermal corrections to a scalar field potential that triggers a phase transition. So let's consider, I would say, simple model where we have a SUN gauge group in the dark sector. And then we have a scalar field, which is our dark Higgs with a potential that is charged under the SUN gauge group. And then we have, for generality, we have also added a dark matter multiplet, which is charged under the dark gauge group. So we have a dark fermion here. Okay, so let's first look at the scalar sector coupled to the dark gauge group. So we assume that we have this kind of Higgs-like potential for the dark scalar or dark NADE boson, if you want. And this Higgs-like potential triggers a spontaneous symmetry breaking of the SUN, the dark SUN gauge group down to a SUN -1. And that happens by having the dark Higgs of the NADE gauge boson. Sorry, yeah.
Yeah, we have 5 minutes left.
Yeah, so the NADE scalar field in the fundamental, and then giving it a VEV in the n direction. And so if you calculate the one loop corrections to the scalar field potential, it looks like this. So in the limit where the effective mass here goes to 0, you get the conformal limit. So you have this kind of Coleman-Weinberg term here, which can give you supercooling. This is an old story back to Whedon in the 80s. In fact, people were thinking that you could have inflation in a model like this, but what happens is that you actually get too much supercooling if you don't break the conformal invariance with this mass here. And so indeed we add this mass exactly to be able to control the amount of supercooling, because we need to not have new early dark energy to fully dominate the energy density, but be around 10% at the time of the phase transition. And then we have the thermal correction from the non-vanishing dark temperature. And then, okay, since time is short, let me be very briefly. So once you have the phase transition here, you have a supercool phase transition, and the latent heat is released from the phase transition, is released into the gauge bosons that are non-abelian, because we assumed an n larger or equal 3. And so you have self-interacting gauge bosons that the latent heat is released into. And that means that you raise the effective number of relativistic degrees of freedom after the phase transition. So you can have that the effective number of relativistic degrees of freedom is close to what it is in the standard model at the time of BBN, so it satisfies the BBN bound, but then it's increased after the phase transition, where in this case, this example is a concrete example where you have an SU3 that is broken to an SU2. It increases the number of relativistic degree of freedom because the latent heat is released into the self-interacting dark radiation, and you get enough dark radiation that you can relieve the Hubble tension in this model. So yeah, so this is just a picture here. And so the second step, the second small increase in delta N effective is from the Higgs becoming non-relativistic. But let me not go into the details in order to respect the time. So then also you have the dark matter multiplet, and as I said, self-interacting dark radiation by itself is not enough to solve the Hubble tension. So you actually need this dark matter multiplet here that interacts with the dark radiation in order to fully resolve the Hubble tension using the Planck data in this model. And since this dark matter interacts with the dark radiation, you have an interacting dark matter component. But after the phase transition, this is a fermion in the fundamental, so it will have a component that is still charged under the unbroken part of the gauge group, so the SUN-1, and then it will have a component, dark matter component, that is neutral relative to the unbroken part of the gauge group after the phase transition. So it's on the chi0 here is the end component of the dark matter multiplet, and that one is neutral relative to the unbroken part of the gauge group, the SUN-1. But because they couple differently, these two, they will also have one loop corrections that are slightly different. So there will be a one loop induced mass gap. And as the temperature falls below that mass gap, which is quantum induced, then the heavier guy, which is the charged guy, will annihilate into the neutral guy, and that means that the dark matter sector will decouple from the dark radiation sector, and so you will have dark radiation matter decoupling at this point. And this is important because, as you can see, if you just have the lambda CDM model, of course you are very far away. The best fit, the minimum in this likelihood is very far away from the Hubble, the Schu's value of the Hubble constant. If you just have self-interacting dark radiation, it helps, you get closer, but of course you're still not fully compatible with the Schu's value. But when you have dark radiation matter decoupling in your model, then you see you become compatible with the Schu's measurement. So in this model where you have this spontaneous symmetry breaking with a dark matter multiplet that is also charged, and you have dark radiation matter decoupling, you can fully resolve the Hubble tension. So if you also add the Schu's data in, so this is fitting only to BAO data DC, the newest BAO data, Planck data, and supernova uncalibrated Pantheon plus data, you see that you reduce the tension with the Schu's data to 1.4 when you sigma, when you have the dark radiation matter decoupling in this model. So this is basically solving the Hubble tension. And of course, once you then also add the Schu's data, your best fit value becomes basically 73 in this model when fitted to CMB Planck data, DC BAO data, Pantheon plus uncalibrated supernova data, and Schu's H-naught measurement. Okay, so let me be quick about the future measurements, or future ways to constrain these models and so on. Of course, once you have a first order phase transition, you have a gravitational wave signal that you can start looking for. Because it's late, it's a little bit low frequency compared to what you would see in pulsars. You can start looking for CMB on small scales that we could do with the newest ACT and SPT data. So this is upcoming work. And then just let me finish with just talking about an important feature here, which is the dark acoustic oscillations that you will get once you have this dark radiation matter decoupling. Because when you have dark radiation matter decoupling, you have something which is very analogous of how you have decoupling of ordinary radiation and baryons in the visible sector. And as you know, the decoupling of ordinary radiation and baryons in the visible sector creates a baryon acoustic oscillation. Because you have decoupling of dark radiation and dark matter in this model, you also get a dark acoustic oscillation analogous to the ordinary baryon acoustic oscillation. So this is the prediction. The dashed line is the prediction of where the dark acoustic oscillation should be. It should be at something like 80-90 megaparsec. And this is the red one is the ordinary baryon acoustic oscillation. And so this is the relative distance between the two in the green line over here. So this is a prediction in this model. So you can actually look for this because we have the DC data. And as you know, the DC data has been interpreted as being evidence for evolving dark energy. We believe this is wrong, that in fact, this is because the DC data should not be explained by evolving dark energy, but instead there is a bias from the presence of a dark acoustic oscillation that biases the DC observations. And the DC observations can instead be explained by the presence of a dark acoustic oscillation, which bias the daisy measurement. And so here is the fit to the daisy measurement using the assumption that there is a dark acoustic oscillation, and you see that you get evidence for a dark acoustic oscillation exactly where you expected also from the prediction from the DRMD model. So this is the most left plot here, where we see the peak in the probability distribution peaking where so this orange thing is from the fit to the daisy data peaking where in the dotted line we have the prediction also from the DRMD model. And so what happens to the CMB BAO tension? It gets resolved.
10 seconds.
Yes. And also if you fit the just the CMB data and the supernova data without BAO data, you get a prediction or you get inferred peak position in the same place as you infer from the BAO independently. So this is independent now. You have two predictions of the position of the dark acoustic oscillation independently from the BAO data and separately from CMB and supernova data. And you can see the likelihoods are peaking in the same place. And so, okay, let me skip this. This is just the matter power spectrum, how it looks with the DAO. This is how it looks in the DAISY DR1 data, just for comparison, if you want. You can see. Yeah, so let me skip also this because of the impatience of the of the organizer, and let me go to the conclusions which are here. Yes. Thank you.